Figaro, Figaro, Figaro. Hey, is that thing on? You know, when I don't practice, I just don't sound very well. It doesn't come out good. The same is true of math. If you don't practice enough of the homework, it's not going to go very well on the night of the big concert. Okay, we're going to have a look at section 13.4, number 19, which we're going to work in its entirety, and number 28, where we're only going to kind of get through the plan of attack stage of the problem. So number 19 says the function of a particle is given by, so we have a vector function, r of t is equal to t squared, 5t is the y component, and the z component is t squared minus 16t. And it asks us to find when the speed is a minimum. So let's, we got to identify the big idea, and the big idea is we want to use speed and optimization to find t where the speed is a minimum. And let's double check that it wanted to know when the speed was a minimum and not where the speed is a minimum. And yes, it does. If we wanted to know where the speed was a minimum, at what point in that trajectory, we'd find the value t, then we plug the value t back in and find out the position in space at that moment. But we're only asked when. Alright, so to develop it, we know that we've got some curve in space. So you could graph this real carefully, but that's not that important for this problem. And we want to find the value of t that minimizes the speed. So let's make our plan. So we want to express speed, and let's just call it the scalar v, as a function of time. And we do that, of course, by taking the time derivative of the position function, and that gives us the velocity vector function, and then we compute the magnitude of the velocity vector function. And then we can optimize v of t. In other words, find dv dt and set that equal to 0, and then we can confirm that we have a minimum. Alright, let's go ahead and execute our plan, our evaluator plan. So the velocity vector is the time derivative of the position vector. So the derivative of t squared is 2t. The derivative of 5t is 5. The derivative of 2t squared minus 16t is 2t minus 16. And now the magnitude of this, which we're just calling v of t, is going to be the square root, and we didn't really leave enough room on that line. So the magnitude is going to be the square root of 4t squared plus 25 plus 2t minus 16 quantity squared. And this is a little tricky, because if you go taking the derivative because of the square root, things are going to be a little more complicated than we'd like pretty quickly. So there's a common technique when you are faced with optimizing something that you're taking the square root of to find the minimum or the maximum, because the minimum of the square root of something occurs at the same point as the minimum or the maximum of that thing squared. So let's let the function f of t be equal to v squared, so we can optimize the square rather than the square root. So we end up with a 4t squared plus 25. And let's go ahead while we're at it and expand out that binomial there. So that would be 4t squared minus 64t plus 16 squared is 256. So let's just double check that I did that expansion. So 2t squared is 4t squared. 2t times negative 16 is negative 32t, and you double it because the middle term gets doubled. And then negative 16 times negative 16 is 256. So now we can combine terms, and f of t is equal to 8t squared minus 64t plus 256 plus 25 is 281. All right, now let's compute df dt. And what is this anyway? When you think about what this is this is a parabola. It's just a quadratic, and it's a right side up parabola. We know it's right side up because the leading term is positive. So it's going to be 16t minus 64. And if you recall, the optimization is the value where the derivative is equal to 0. So that occurs at t equals 4. So the answer is, when is the speed a minimum? Well, the speed is a minimum at t equals 4. So how would we assess? How would we double check? Well, if we graphed, not the original function, but if we graphed v of t, we should be able to visually inspect the graph and see that this function here has a minimum at t equals 4. So when we graph it, we'd get something like this. So by visual inspection of the graph and confirming that the minimum occurs at t equals 4 would give us confidence that we've solved the problem correctly.